It's my great pleasure to have Rodrigo Castano from University of Buenos Aires visiting us. He's a PhD student there and working on making model checkers more accessible to users, and look forward to the talk. Welcome.
All right, thanks. Thank you for the introduction, Shuvendu. And okay, I'm going to be talking about, explaining inconclusive outcomes from software model checkers to users. And this will mostly cover my PhD work, and it'll extend a little bit into the future with stuff that I would look forward to do in the next few months/years. So let's start with motivation. So why do I want to care about inconclusive model checker results? Well, because I might want to check any of the properties that you have on your right, and we have assertions in the code, and we have assertions of invariance, and it's just regular C code. We're not dealing with models, we're actually dealing with source code. And I might choose a software model checker that I like. I might choose a set time limit that I have. Maybe it's like 1 minute, maybe it's 15 minutes, half an hour, whatever time. I run my software model checker, and then I come back and I get unknown, time limit exceeded, or maybe memory limit exceeded, or maybe I had an abstraction refinement error, or any of those things. Or maybe I'm using a bounded model checker, and I get, well, I didn't find a bug, but I've reached the bound, so it's still an unsound result. So what do I get from this? This is not a really useful result, because what do I do next? Do I extend the time limit? Do I trust the code? Can I trust the code? Can I just like commit this code that doesn't have any tests and just use it like this? Should I change the technique? It's not really useful, right? So I feel like this is a topic that actually requires attention, and I think it could have an impact, and we're going to talk about how it could have an impact. So let's take a step back. So we have basically two ways of seeing verification/bug finding, right? So we have bug finding techniques such as bounded model checking, fuzzing, the dynamic symbolic execution, and all that. And basically the workflow is you test your system until basically you've tested enough, and you assume that your system works, right? You put it on production, it runs, and then, well, if it has bugs, it has bugs. But then you have the opposite, sort of. And obviously, usually, the type of systems that are tackled by each of these techniques are different, right? That's why you also have different baselines. So if you're working with assisted or automatic verification, but you're trying to have full verification, maybe your baseline is, well, my program might have bugs unless I find a full proof that the program is safe, right? So what you do is you attempt verification, and maybe you time out, or you get some counterexample that's spurious, and then you simplify the property, and then you simplify the program or refine the abstraction. Essentially, you work on the instance of verification, then you try again. And if you can't manage to get a conclusive result, then you basically assume that your program is not safe, because you don't have any guarantees. You don't know how far your model checker went, right? So both of these approaches have, sorry.
Are you talking about user-assisted verification? How does this fit in there?
Yeah, sort of. If you're,
Manual verification.
Assisted. So if you're working with, for instance, Daphne, right? And you have to add invariance or whatever, and you get a timeout and stuff like that. Well, you're trying to simplify your properties and maybe just look under the hood. Why is it timing out? And then you split your properties, and then maybe you add invariance and so on and so forth. But unless you have a full proof, you won't say, okay, well, I've tried good enough. I've tried for like maybe 2 hours. This must be good, right? Usually you don't do that. That's not the workflow that most people follow.
So you're saying that the problem is you have a black box, and it's timing out, and you don't have a good explanation for why, and so you're hacking it. You're like, oh, maybe if I. Is that the process you're describing?
No, not really. What I'm saying is that
you're trying it.
Yeah. So what I'm saying is that usually, if you're an expert user, you will have some insight as to what you're supposed to do. But unless you reach a full proof, you won't assume that your program is safe. You won't get halfway through the proof and be like, I'm pretty sure this works. Usually, when you're doing that, you won't assume your program works, right? Sorry.
If you're using Daphne, then the expectation, I think, is you have a property and a program, and you're trying to prove.
That's right.
Right.
Yeah.
So if it's timing out, the assumption, right? The user assumption is like, oh, I haven't gotten a proof yet.
That's right. Yeah. So
But I don't know. I mean, I might have all the information. All the information might be present. It's just like the theorem prover is not good enough to do it right now. I have to do something.
that's right. So what would you assume about the system is sort of my question. Is would you assume that the program is safe to use? Would you release it into production without a full proof? Do you have any notion of how far you got? So, yeah, sorry.
Yeah, so what about the case where there's a property that I know holds as a programmer. I know that property holds, and I
Right.
just and it can't prove that property. So
Right.
I could just assert the property is true.
You could
That way the proof would go through, but assuming that it doesn't time out for some reason, which that's a whole different category of issue. But
Right.
but the point is, I think that the human can get in the loop in the sense that you can help the theorem prover by giving it sort of extra information that the programmer has, but the verification system doesn't.
That's right.
That's what
But
he means by simplify the property.
Right.
So adding an assumption
would
for
simplify.
something you know would be simplified.
Yeah. Okay.
Yeah.
Okay. So, but at that point, then, why would you stop in some sense? Because you could always give it enough information to complete.
Yeah, no.
proof,
The
right?
question is, at some point, maybe you think that a property holds, but you're not absolutely sure. I mean, if you know that a property holds, you definitely add it to your assumption, and then you have a conclusive verification result. But if you don't reach that point, if you keep iterating on this, and you're like, okay, I'm adding assumptions that I'm not really sure hold right now because I don't really know what this library does or like this other thing, then maybe you want to know, well, are my assumptions too strong? Like, when does this assumption actually affect me? Like, is this relevant to my system or not?
Okay.
Right? So, problems? Well, bug finding and testing doesn't really have that many guarantees because, I mean, you're testing. So if you didn't find a bug, you don't know whether there exists one or not.
But it has a guarantee when you find a.
Well, you have if you find one, yeah. But if you haven't found one, you don't have many guarantees. And the problem with the other approach is that, well, it's kind of all or nothing. If you follow that idea, that paradigm of, okay, if I don't have a full proof, then I'm not going to give up, then it's kind of all or nothing, right? If you didn't manage to make the whole proof, all of the effort that you spent on it is wasted, and you have to start over with whatever other technique you're going to use. And then, to be honest, there's not that many people using this sort of techniques, right, in industry. Basically, testing is way more widespread than formal verification techniques in the sense of trying to achieve a full proof. So what if we take a different perspective, right, and we use this sort of verification tools, but we use them in a way as okay, this could be better than testing, right, but I want to know how good it was, right? And let's assume that Visual Studio checked every assertion, memory safety. Now I'm doing a little bit of science fiction here, right? But suppose it checks all of these properties, system API specs. Then we have a dashboard showing us how good the verification attempt was, right? So we have maybe on the left the things that were properly checked, that we got a complete safe result, and we have a proof that it holds. Then we have on the right maybe the warnings, and we could have different kinds of warnings. We could have warnings that might be false positives, and then they can be ranked according to how likely it is that it's a false positive or that it's a true positive. And then in the middle, we have sort of an explanation of what your model checker did, right? What sort of behaviors did it cover? What part of the code did it cover? Do you have like any like code coverage things? And maybe suppose this is all integrated into the code review process. And instead of asking your developer, okay, whenever you check in code, I want you to test your code, maybe you have a separate dashboard that goes, okay, well, this was tested in the backend in Azure, and all of these parts of the code were actually tested. And the parts of the code that were not are these edge cases. Maybe that would kind of change how we use verification tools, right? And okay, I said I was doing a little bit of science fiction, but honestly, what parts of this are not present yet? We can already check all of those assertions, and if it is fully verified, that's the column on the left. We can show that, right? And then we can definitely produce warnings. We can produce warnings with different levels of guarantees. And we can also rank them. We have angelic verification. We have almost correct specifications. And all of that allows us to rank different warnings, right? But we don't have the stuff in the middle. We don't really explain what happened in the cases when we don't have a warning, but we don't have a full proof. And that's a lot of cases. So maybe if we had that, and just maybe, that might be the one element that keeps all of the rest things together and makes it reasonable to integrate it into a mainstream IDE like a Visual Studio, right?
So you're saying this coverage comes purely from the verifier, not from our testing?
It could be a combined effort. It could be a combined effort of maybe your testing plus whatever verification efforts you have. But essentially, you would have an idea of what parts of the code were not actually exercised, what parts of the system behaviors are not checked yet. So okay, this was a little bit of wandering around in my mind, but let's talk about how my PhD work fits into what already exists and how is that a step forward or not. And okay, let's start with two papers that are actually from my research group. The first one, my model checker died, how well did it do? What it does is basically it gives you a measure. It gives you yeah, pretty much. That's what you're asking. You know? So what it gives you is a measure, a probabilistic measure. Why is that? Because it tackles probabilistic model checking of Markov chains. Right? And what it asks for the user is a usage profile. So you need to give it some idea of how the system is used so that it can tell you, well, if that's a probabilistic distribution of methods or input or whatever, then this is how much of the state space you have explored. So that's asking a little bit too much of a software developer, but also this does not really scale that well to software model checking of actual source code. Besides, it's super sensitive to those usage profiles that you provide. So it's not ideal. There's definitely room for improvement. Then Alloy plus Hotcore. Alloy is a specification language that is specifically suitable for structural properties. So it's good to specify maybe data structure invariants. And the way it works is it bounds the constraints and then it translates them into propositional logic and then it checks them with a SAT solver. And the idea behind this paper is essentially, okay, let's try to get some statistics on which variables and clauses are involved in most conflicts and lift that up and show it to the user so that the user can pay attention to those and maybe organize them in a different way. So it's kind of heuristic and it's limited to Alloy. It doesn't necessarily apply to other types of techniques and languages. But anyway, this is part of the stuff that we're building on. And then the most related work is basically conditional model checking, which I work on top of, basically. And then explicit assumptions, which you probably know because you had Maria Christakis here. This is, I think the original paper was collaborative verification and testing with explicit assumptions or something like that. And then bounded upstream interpretation, which I'm not going to mention much, but it's basically built on top of explicit assumptions. And let's talk about conditional model checking a little bit. So we have this example, right? And the true branch of the code can be easily proved safe using some sort of predicate abstraction. Why is that? Because we don't need to sort of unroll the loop too many times, right? If we track the predicate I is greater than or equal to 1,000,000, then it's easy to prove that the true branch is correct. However, if we're using predicate abstraction, the nonlinear condition on the false branch of the if might be hard to prove, right? So your model checker might give up. Right, so what they propose is, okay, it would be good if that failed attempt could sort of give some of that knowledge forward to whatever subsequent verification attempt, right? So what they propose is, instead of having model checking have three possible results, true, it means that the property holds, false means that there's a counterexample and it produces it, and then unknown, maybe we can only have false and then true under a certain condition. That's their general idea, right? So that subsequent verification attempts can use that condition to sort of constrain their state space.
So is this done prior?
Yeah, that's right.
Okay.
So that's the general approach. Now they instantiate that for a particular kind of analysis, and that's abstract reachability trees. And what they produce, their condition, is an assumption automaton. Right? And I'm going to talk a little bit about assumption automata and abstract reachability trees in the next few slides because it's relevant for my work. But let's just look at this example for a second because I think it's really easy to follow what's going on. So we have an edge that goes from the root node to the node labeled true, right? And that edge is labeled by the condition none dead, basically holds. So that means if you enter the den branch of the code, then you're safe. The true node means that all of that portion of the state space has been verified. So whatever subsequent analysis does not need to check that. So this is useful because maybe you're using explicit value analysis afterwards, and then that would get stuck in the loop if you couldn't discard that whole state space. So that's an interesting idea, right? So that's basically their use case and how they show that it could be useful. And now, let me explain a little bit how abstract reachability trees work and what they are.
So was the other branch not interesting for us to look? It's just,
The false branch?
yeah, the other side, the else branch. What was happening
Yeah.
there?
Yeah, so the else branch is sort of unrolled in a way because it couldn't manage to. So the thing is, the model checker had trouble getting rid of the spurious counterexample, right? So it has a nonlinear condition. It has an assertion that says that R is greater or equal to X, and R is X squared. So it's always going to hold. But since it's nonlinear, it might have some trouble getting rid of that counterexample, right? So what it does is when it cannot refine the abstraction, it gives up. And it gives up telling you, well, I explored everything, but I have this part of the state space that I haven't explored because I couldn't get rid of it, basically.
So false means that it is possibly false?
It means that it hasn't, that part of the state space has not been explored. I'm going to explain this in a little bit more detail after I explain abstract reachability trees, because otherwise it's kind of hard to follow. But, yeah,
Just
sure.
to go back a little bit. So does this actually happen in practice? Like, I mean, what are the kind of situations where, you have that kind of result? Is there a literature that says that it's a common thing, or that,
In the paper they have an evaluation with SVComp instances. I don't know if that happens a lot in practice, but then again, it's sort of a chicken and egg problem. Like, we don't really use verification that often in practice, and then SVComp.
Do you mean failing to verify or specifically a non
well, that if you had this, that verification could help you part of the code, but then there are these other
That
parts.
happens every verification, almost everywhere. Yeah.
So does that mean that verification generally doesn't work? Because otherwise you'd want to have this, right?
It works very few
No,
cases,
it's true.
but
Oh,
yes,
okay.
usually that's where you get false alarms.
Yeah,
it's
well,
false alarms, right?
I guess it comes down to,
It's
right?
how many of these you have.
Right.
Yeah.
I think it's very frequent because the parts of code that are very complex and you just show lots of false alarms in that part of the code. But I think what it
Okay, but basically, if I think of it abstractly, I can have a whole set of different analyses, and the abstract reachability tree lets me basically say what this analysis was able to prove true, and then where it basically wasn't able because of whatever imprecision. It could be it could be imprecision in the abstract domain. It could be a timeout. It could be, but whatever it is, you can sort of summarize the state space of what was explored and proved true, and then the rest.
Yeah, that's right. So that's our idea.
And then you take this thing and you can pass it on.
Yeah.
Or it's a representation. This thing may be huge. The
This thing
representation.
is huge.
This
Yeah.
thing, like we did this in Slam, right? We had the model checker, we had a BDDs, and yeah, we could persist the BDDs, but somehow we never really did that for some reason.
Yeah.
We learned a lot through the state space, but yeah, yeah. Okay.
Yeah, I agree. It is definitely huge. But anyway, so that's their use case, and that's how they show that it could be useful. And abstract reachability trees, basically, you probably are familiar with it, but I'll just go over it quickly just to make it self-contained, are trees that where its nodes correspond to a state in the counterflow automaton of the code, and its edges are labeled with statements. And the way it works is it keeps a wait list of nodes that haven't been explored yet. So these are the ones in orange that have the big arrows that say unexplored. Then you pop a node from the wait list, and then you add its successors to the wait list, basically. That's what it does all the time, until it finds a target node, right? So in this case, the red node, the node 7, is an error node. The thing is, it's an unfeasible error node. And why is that? Well, because the path that it takes is, it assigns 5 to I, then it checks whether I is greater than 0, and it goes on the false side of the condition. And that cannot happen because 5 is greater than 0. So that's the reason why it's not feasible. Then it goes on, and then it reaches the error condition. So what do? We associate to that node in the abstract reachability tree a predicate. Why is that? Well, because abstract reachability tree nodes are associated with an element of an abstract domain. That sort of makes them versatile. But if we had, for instance, BLAST is based on abstract reachability trees, and their domain is the predicates, right? So we add that predicate. And what happens next? Well, that defines implicitly a reachability region, right? So we will be able to get the whole subtree that hangs from node 4 and remove it, right? Because we know that the predicate no, that I is not greater than 0 does not hold under the node 2, right? So we remove that. What do we get? We get this, right? So we only get the unexplored node 3 in the wait list, and then we pop it, and then we add its successors, and we have another node, and then we pop it, and so on. So if we finished right now and we timed out, then our assumption automaton would look pretty much like this, but without the predicate in the node 2, right? Because assumption automata only exposes the structure, but not the domain elements. So basically, that's an overview of conditional model checking and abstract reachability trees. Now let's go with explicit assumptions. So what they do is propose an extension to the specification language such that we have something that behaves a lot like assume statement. Sorry.
Go back to the.
Yeah.
So
sure.
what is the property of this abstract reachability tree? That if there is an error in the original program, there is one in the
in the full abstract reachability tree, but you're building it on the fly. So yeah.
I see. So this is.
So-
I see. This just says where you left off. It doesn't say
That's right.
the rest. Okay.
Sorry, what do you mean the rest?
It's not the complement of what you verified.
Not really a
It's
complement.
the
No, I mean,
right. It's
it will represent. So basically, the property of the abstract reachability tree is that every system execution will every feasible system execution will either lead to a node in the wait list, or it will lead to a true node. Basically, that would be the property of the assumption automaton that you produce. So it's an over-approximation in that sense. Then we have explicit assumptions. And what's the use case that Christakis had in mind? Basically, it's a good way of annotating what unsound assumptions were made during verification. So one good example, is that there's no integer overflow, right? We have unbounded integers. So it's pretty clear. Like if you're reading Daphne and then you get this assumed statement, you might realize, oh, wait, in the language that I'm trying to model, maybe I do have integer overflow, so I might need to pay attention to this. These annotations are really useful for local assumptions. They're maybe not that great for the type of assumptions that you make, that you want to capture in conditional in assumption automata, right? Why is that? Well, because for instance, when you have loop and rolling, and they actually check this in their paper, in the explicit assumptions paper, it's kind of hard to express this. It's actually impossible to express it just with the assume statements. So what they do is they have to transform the loop. So you have to transform the code in order to add these assumptions. But then again, I feel like there's room for improvement, right? So it's what we were talking about before. You add an assumption that you might not be sure whether it holds or not, and it might be buried deep inside your code in some obscure function that you sometimes call. And you wonder, well, when are these assumptions broken? When do they hold? Is it relevant that I added this assumption? Is it not relevant? Anyway, so yeah.
Does the statement here means the loop has to enter at least once? That's what the assume not see.
Yeah. So some analysis, what they do is they unroll a loop once, and they assume that the second time you don't enter, basically. So it's bounded model checking to once, basically, with one iteration, right? But if you want to do this for more than one iteration, then you have to unroll it in the code, and that's not ideal. I think that makes it way less understandable. So there's definitely room for improvement here, right? Because you don't know how relevant these assumptions are. And then the same thing happens with conditional model checking. Let's go back to what we said before. You asked me, well, what does it mean that you have a false state here? Well, it means that you...
Back to the previous one.
Sorry,
Right.
yeah.
So I think these assumes are manually inserted, right? They're not automatically.
No, they are. Yeah. So that's one of their studies that they did, was basically checking how relevant these unsound assumptions were across different model checkers, which is part of the soundiness manifesto paper and so on. Anyway. So back to conditional model checking. Well, is this a perfect solution? Well, the thing is, suppose you expose this to a user. Well, first of all, yeah, it's going to be huge, which is what Tom mentioned. But other than that, you see a false statement, and you might be wondering, well, how relevant is that false statement? Well, it's not really relevant because it's not reachable there, right? So you need to do something about it in order to interpret it. So basically, this is where we start from. So what is my approach? Well, we have two different approaches. One of them is execution reports. So what we do is we present a report that captures safety assurances in terms of system executions and the relationship to the safety property of interest, right? And then we have another approach, which is coverage, which is sort of the opposite. Meanwhile, while execution reports aim for detail, coverage aims for succinctness, right? And it is an intuitive definition. It's comparable to test bed coverage, which is interesting because you get a way to compare it to entirely different techniques. But they're kind of complementary. So let's start with execution reports. So as I mentioned, what you do is you create a report based on system executions. And concretely, what we do is we provide two sets of system executions. One is the exploration frontier, and the other one are the safe cones. Essentially, if you've already followed the whole part about conditional model checking, what we try to find is paths that are feasible that lead to the true states and the false states. And what does it mean for an execution to be in the exploration frontier? Let's look at the example on the left. We have a verification harness that exercises the two operations of a stack. We have push and pop. And then it non-deterministically chooses the operation, it calls the function, and then it checks whether the invariant holds, right? And it does that forever, basically. So what does it mean to have the execution push in the exploration frontier? Well, what it means is that that's the precise point where the analysis gave up, right? So when it was reaching the second push call, it had to stop for whatever reason, timeout or anything, and then it didn't explore that system execution, but it didn't explore any of its continuations, right? Any possible extension of it. And the same holds for push pop, right? So if you just finished your model checking attempt and you left it for half an hour, would you be like, okay, ready to go to production? Maybe you wouldn't, right? Because you're like, you didn't check any of the border conditions that I might be interested in. Right, so this is, it's not great because you still have to do something. You have to test your system or something, but at least you know that your model checking attempt was definitely not good enough. And what might happen to you if you're using, for instance, a bounded model checking technique is that, well, you get the idea that, okay, it didn't present you any warnings, but it didn't really go that far because whatever, it couldn't skip some loop or something like that. Anyway.
But don't you run into the same problem here? The model checker is going to do a lot more. So isn't your exploration frontier going to be also huge?
Well, that's a great question, and actually it's not. But it depends. It depends on what instances you're looking at.
If it's a set of traces, it seems like it can be a very large set, and many of those traces are sort of similar to others. You're trying to sort of summarize an exploration which inherently, can be, the program is size n, and this can be exponential in it. Right?
That's true.
Right. So it seems.
I can talk about that a little bit. Yeah.
Okay.
Please.
Yeah, I had the same question. I guess with bounded model checking, the underlying assumption is that with even a small, like if you're doing concurrency or something like, even with a small number of threads,
right,
you're going to find bugs.
Right.
You're not going to find the bugs when there's 16 threads because it's way too far. But the whole point of stopping is that if you keep going, it's going to get the state space is going to get bigger and bigger.
Right.
Right. And so it seems like this frontier that you're talking about would just get exponentially larger. It's like Tom was saying. And what would a person do with that at that point?
That's kind of true. Let me talk about that first, and then I'll talk about Tom's observation. So first of all, the thing is with bounded model checking is that you have that assumption, but that's a very general assumption. So one of the things that inspired me actually to start doing all this is that I did an internship here, and I was using Corral. And one of the things that I kept doing all the time was adding false assertions to know how far my exploration attempt went. And I was like, it's true that, shallow bugs and all that, but how far did it go? Did I get after the initialization loop?
So basically, can you prove this assert false for me? You sprinkled assert false.
I would sprinkle assert false after certain loops because I was like, I don't know how many iterations this can have.
Can you even get here?
Can you even get here?
Okay.
Yeah. Okay.
Right,
So what
sure.
you're saying
It's a smoke test.
That's a coverage. So that's a coverage.
It's hard to know what happens.
It's a smoke test, but
Yeah.
I'm not the type of super novice user. Still,
Right.
I had to do some really kind of dark stuff to make sure that the model checker was doing some of what I wanted it to do, right?
Yeah. Okay.
So it's true, but it's still we need at least a tiny window into what's going on inside
The
that.
model checker can at least do statement coverage for you, right? Because when it explores the statement, at least it reached it, and you can say just like a test, because it's fundamentally executing the code. Even if
We're going to talk about coverage in a couple slides.
okay,
Just
so,
give me
so the
2 minutes.
frontier, but the way you've defined the frontier is a set of traces, right?
It's a set of traces. That's right.
Okay.
And your question was actually really good. So you might have an exponential number of traces. That's true. One other thing is we don't say that we're going to present the whole set of traces. We say that we're going to present some. And why is that important? Well, first of all, because if you see one trace that is too short, you might already realize that your exploration is not deep enough. That's one of the things. And then your other question was, well, you might have a ton of traces that are very similar. Why is that? Well, because inside the push, you might have an if whatever condition happens, then and you have one path that goes on the true condition, and then another path that goes on the false condition, all that. So that's true. And that's a problem that we actually don't tackle explicitly in our paper. I did tackle it in order to look at the output. And what I do is basically I group those traces. What I look at is, for instance, in this case, API operations, right? So it's true that I don't get the full, detail. But if I know that I didn't do more than 2 loop iterations of the main loop, we would probably agree that that's not a very deep exploration. Well, for none of the examples that I checked in the SVComp benchmark, I had never reached the 3rd iteration of the loop. Right? So it does actually happen that you don't really get that far. And it really depends on how non-deterministic your instance is and so forth. But it's not entirely crazy to have this sort of instances.
So I guess if you're saying that these traces, even if they're abstract projected on some API, they cover the actual ART, then you're okay, right? Because there might be some spurious traces in there.
That's right, yeah.
But that's okay, you still know that you never covered beyond 2 pushes, right?
That's right, yeah.
And that's, I think, is valuable.
Yeah. That's the sort of insight that we want to get. And then we have safe cones. And what are safe cones? Well, this is essentially paths to the collapsed part of the assumption automaton, right? So this is the true nodes. It's those places where you manage to prove that something was safe. And let's see it with an example again. So we have a verification harness on the left that non-deterministically chooses the mode of operation of a system, right? And we have mode 1 and mode 2. And our original verification result would be unknown, time limit exceeded, or something like that. What we get now is, well, the system execution that only calls mode 1 is a safe trace. What does that mean? Well, it means that your system is safe to use under mode 1, because any extension of it will also be safe. That means that there's no assertion failure. That's a very strong statement. That's much better than what you would get with testing, and much better than what you would get with an unknown result, right? But it's also detailed enough to tell you that, well, even though mode 1 has been very successfully proved safe, then mode 2 was not so good, right? Because we get pretty much the same case that we got before. We didn't get past the first iteration of the while loop. So it gives you some insight into, well, maybe you can remove mode 1 from your verification harness, and then maybe you can pay attention to mode 2 and probably use another technique because you're not making progress with this. Right? This is all very manual, though. I do admit that. It's not like we're going to get a tool working right away. Sorry.
I think for the safe, you want to give an under approximation, things that you're definitely sure about, right?
That's right, yeah.
Okay, so.
Yeah. So, we're not going to go over each of these formulas right now, but what I want to emphasize is that part of the work is that we formalize what the guarantees for each of these parts of the output are, and what are the connections between our output and the safety guarantees, because I think that's relevant for making it intuitive and understandable. But what we are going to do is go over these formulas and how they apply to the previous examples, right? So we have the first example in which we saw the exploration frontier. And what does it mean that we have push-push in the exploration frontier? Well, it means, A, that it's feasible, right? It's an actual system execution. You don't have to go checking, well, can I actually ever do 2 pushes in a row? No, we actually check that for you because that's the reasonable thing to do. But then we also know that whatever safety property you were checking for holds, right? That means that your analysis is sound. If there was a bug in that trace, we would have found it. And then you know basically the same thing that you would know for a test case, right? If you see a test case that passes, you know that, well, it didn't fail, which is kind of intuitive, but still. And then you get that it's a maximal, right? So that's the exact point where the model checker stopped analyzing. So you know that that's basically where the frontier reached. It's not like, well, you might be exaggerating or it might be more than what it actually reached. No, that's the exact point where things change from being analyzed to not being analyzed. And that can give you an insight if you know sort of something about the technique, the underlying technique. What about the safe cones? Well, safe cones, it's pretty much the same thing. We have, they're feasible. So actually you can use mode 1. It's not impossible to use it. And then it's minimal. So it's the strongest guarantee that you can have. And also, well, it is a cone in the sense that we have the property, well, if a trace is a safe cone, any extension is a safe cone, which is the one over here. And well, if it's a safe cone and it's feasible, then the property holds, right? That's basically it. So yeah.
What's an example of like if you do this operation, you're guaranteed to be safe? What?
Sorry?
Like what's an intuition that if you do mode 1, you're guaranteed all extensions are safe?
Yeah.
Like how would that appear? And like what does it correspond to in real software?
Even in a verification instance, it would be pretty much the example that we had at the beginning. That we have so basically, if you have some weird optimization in your mode of operation, and that makes it super hard to model check it, whereas the other one is straightforward but is just super inefficient, maybe it would be easier to check. That's sort of the motivation. Obviously, chicken and egg. We don't really have big verification instances that do not check manually and so on. So well, anyway. So what are the research questions? First, is this, so yeah, sorry.
So Maria Christakis has looked at this relationship between testing and verification.
Mm-hmm.
And well, one of the things I think she explored was this issue of if I can verify this part, then I only have to test the other part.
That's right.
How does that relate to this?
I mean, it's pretty similar. It's the difference is that the goal of this is to show it to user. And basically, in the case of Maria Christakis, she's writing tests, and maybe you would have to look at the tests. That would be your goal. It's kind of related, but it is different kind of analysis. Also, the type of annotations that she has works for a specific kind of techniques. It doesn't really work for the same techniques that I'm trying to tackle.
Okay,
so I mean, it's complementary.
I don't know that she was doing model checking, for example. I don't know if that's true.
And she was using Daphne. She was not using like whole program model checkers. She was using modular stuff. So it's a slightly different use case, basically. So research questions. Well, is this practical performance-wise? So as you might be picturing already, what we have now is several verification tasks. We came from one that didn't work well, and now we have several because we need to produce several counterexamples, right? So this might very well be no, the answer to research question 1. And then research question 2 is kind of related to what you asked before. Is this going to be an exponential number of traces? Is this going to be manageable by a user? Ideally, we would want to test whether this is understandable and useful. I have to be honest with you, we're not at this stage yet. We don't have a clear use case that we can conduct a user study and be like, okay, does this work better than what you had before? Again, chicken and egg, we're not using verification for anything, so it's kind of hard to tell. Architecture. So this is how, sorry.
You don't have a, I thought you were using SVComp.
Yeah.
And you have some benchmarks.
We have benchmark, but we don't really know how to conduct a user study that would be a realistic use case that is already a use case. Because you don't have any way to look into verification results right now. So you can't really outperform that.
But you can show that you find new things, or you give insights.
Yeah, what we have is anecdotal evidence. So what I do is I go and check the output and say, well, you didn't know this before, but I don't know if that's not a user study, that's a author study, right? So conducting a user study means you have a user, and you don't really have users of similar techniques right now. That's kind of the problem.
So did you do author study?
Yeah, I did. I went through every single output.
You're going to present?
Okay.
And I'm not going to talk about the author study because that's not in the published paper, but we can definitely talk about it in the questions, yeah. So our proxies is at least, are they manageable in size? Because if it's not, then why bother, right? So this is the architecture. You have a system under verification. You run it through your software model checker. That's abstract reachability tree based. That produces the assumption automaton, which is the abstract reachability tree structure. And the input for the two verification tasks is the system under verification and the RT structure, right? And they're different and they're independent in that they have different targets, right? In one, we're targeting the states, the nodes in the wait list, which is the one that produces the frontier, the exploration frontier. And then in the other one, we're looking for the collapsed true states in the assumption automata, which are the safe cones. That's why.
So wait, so I'm
Yeah.
a little confused. So you're doing 3 model checking then? Or you produce the art and then you have another model checker, so I
Yeah.
don't quite understand. So
Yeah, let's go over again.
So if you're applying the same model checker to art gives you the model checker did something.
Yeah.
It gives you an art,
Yeah.
and then you ask it to explore more from those states.
You ask it to explore your verification instance. Essentially, what it does is it composes the system with the abstract reachability tree,
Yes, I understand.
right? And then you try you
Which
make
is basically
queries.
the result of running the first model checker.
Basically, yeah.
Okay.
And then you make queries on top of that and try to see which of those states are actually feasible or not, because you're interested in the true states and the false states.
So, but do you? Okay.
One detail about this is it doesn't have to be the same model checker for like those 3 boxes.
Sure.
Yeah.
That makes a little more sense because I was just wondering, well,
You're gonna
how are
repeat
you going
the
to find
same.
any new information?
Yeah.
If those 2 are the same one.
Right.
Okay, so this might be the case of like Daphne and some other like DSE. Like I might have different notions of checking whatever the checking are, right?
But the first time when you run the model checker, you don't have the art structure to start with.
No, I
Yeah.
understand
Yeah,
that.
so you're actually
So the
doing
second
different
time,
tasks.
no, I mean
Yeah.
reading the diagram. It's just I'm just saying if you give like the end result. Well, maybe you give it more time and it can discover more. Okay.
It's not just about giving it more time. It's a different property, so it's going to be a different exploration altogether. Because you can have an
But it's
abstraction
conditional because it's based on the.
Yeah, no,
previous-
absolutely. But since it's a different structure, it could trigger different abstraction refinements because of that. So it's not the exact same exploration. But I do agree, and there's actually results in the evaluation that.
Okay, cool. So
Yeah.
you could the model checker might have many different parameters,
Yeah.
and like the second time you do it, you might tweak them.
Yeah,
Right.
absolutely.
Okay.
But if I understand
Sorry.
the picture, you're essentially querying the art using these 2 model checkers. You're asking some properties in the art,
That's right.
as opposed to the original verification, which was checking some property.
That's right.
This is saying which part is really covered, which part is not covered.
Mhm.
Okay.
That's right. So what we do is we run this on 68 instances from SVComp. These are the instances that the conditional model checker paper presented. So we should try to not have any selection bias in that. And then we use 2 techniques, value analysis and lazy predicate abstraction, which are very different in themselves, and that's kind of shown in that they time out for almost entirely different instances. And then phase 1 of the evaluation is we run this with a 900-second time limit. We run both techniques. And then for those instances that produce inconclusive results, we run phase 2. And we generate execution reports, right, with the same time limit, both techniques again. So we have basically first value analysis and then value analysis, or first value analysis and then predicate abstraction, and so on. You see, there's 4 combinations, right?
So should I understand phase 1 to be the leftmost box in the previous slide?
The thing that generates the art.
It's the left one. Yeah, that's right. And okay, what are the results for this? Well, we get 9 inconclusive results with value analysis in the first phase, right? We produce a full, and then full means something. I'm going to explain what full means. Frontier reports for 5 of those instances using lazy predicate analysis. And the average size is 12.2, ranging from 4 to 30. It's not huge, it's manageable. Then
The average size what?
of the execution reports, and then the number of executions in the full frontier set.
Oh, this is number of traces. Okay.
Yeah, that's right.
But how long are the trees, each of them?
They're very long. I'm going to talk about that in a second. Yeah, and the average time limit is 78 seconds. That's kind of good, right? Because it's less than 10% of the original verification time.
Can you go back to the previous slide?
This one?
So what are the sizes of these code bases?
The size in terms of lines of
Yeah,
code,
lines of code.
it's about 1,000 lines each. It might be somewhere a couple hundred, somewhere a little bit over 1,000. They're not huge.
Okay.
Yeah. So yeah, so that's for value analysis. It's not great, but it's for more than half of them you can produce a report within a fraction of the verification time, right? So for value analysis, then we get the safe component of the report. We were talking about the frontier component. Now we're talking about the safe component. Same, we only produce for 5. curiously, it's not the same 5, so it's not like you can produce a full report for the instance. And here the average size is low, right? It's just 1 trace. It goes from 0 to 2. It's not much, and then the average time goes up significantly. It's still, since we time out at 900 seconds, it has to be less than the original verification time.
So is it the same set of 9 that gave inconclusive results? It's
It's
really a property of the program,
Yeah.
No matter what kind of analysis you're doing. Wait, the first one was value analysis.
No, this is both.
This is both value analysis, but it's 2 components. It's frontier.
It's the frontier versus safe. Okay,
Yeah,
I get it.
that's
Okay,
right.
now I get it. Okay.
Okay.
Yep.
And then we move on to those that timed out with predicate analysis, right? And we get 16 inconclusive results, and we produce a full frontier report for 13 of those. And curiously, again, it works better using value analysis to produce the reports, which is what Tom had Dane said about. So the average size in this case is not that good. It's 118.3 traces. That's not what I would describe as manageable, right? That's a little too high.
Can you just, I'm sorry.
Sorry.
I know lazy predicate abstraction. What is value analysis?
Value analysis is you keep track of the values of the properties, the values of the variables. So your predicates are equality.
Oh, I see. Okay.
So you do a lot of unrolling basically, because you're going to have a different node for each iteration of the loop usually, because you increment the value and then you have a different node.
Yeah, I see. Okay.
So average size goes up. Average time still is pretty low. It's a 10%, but it can go up to 629 seconds, which is not that low. Still, 13 out of 16, given that we're doing several.
So what, did you have an upper limit on the time? So 900 seconds was the upper limit in both cases. Okay. I see.
Yeah. So you can't go over that. That's what I was saying. Yeah.
So, but none of them actually failed in the second phase. In the sense of not actually finishing, right?
No. Yeah. Because
because you only get 5.
Yeah, you only get 5. So 4 failed.
Okay.
4 didn't produce.
Okay, yeah.
4 didn't produce a full report, and I'm going to talk about that in a second. I'm sorry, I don't know where it was. Predicate analysis, full frontier. Here, safe reports, same. 13 is not the same 13 though. And again, what works better is value analysis, right? And the average size in this case is not great. It's 0.07. So it means that for 12 of those, it was 0 traces, and then for 1, it had 1 safe trace. And we're going to talk about this in the sort of conclusions of it.
So when you say 0, it just basically gives you no information, right?
It finished and it proved that there was no safe trace that was feasible.
Well, what that means, you are unable to capture any abstraction that is
It's
safely extended, right?
That's right. It means that the first attempt did not prove any fraction of the abstract reachability tree safe. Any feasible.
900 seconds, why give the same time? You might, right, you could
Give it
decide-
longer?
Mhm.
What do you mean?
So, I think your intuition is that you don't want to give it too much extra time because the model checker would have discovered some more, right?
My intuition is this is a post-processing of the verification time. And if I'm going to give it 5 hours, I might as well give the verification time 5 hours. So yeah.
But why 900? Why not 90 seconds? I would.
I feel like it's an arbitrary limit. Yeah. It's just I wanted to see how basically if it's more than the original verification time, I feel like it's no use of producing a report that takes longer than the. I don't know.
Sure, but he's asking why did you choose 900 for the original verification?
Oh, that's standard for SVCOM, so I just used
More
that.
concerned
you
about
were-
the 900 for the
For
second.
the second,
phase.
oh, okay.
Yeah.
Because it's a post-processing, right?
Yeah.
Yeah, you might think, well, I should give it 90 seconds.
90
Just a little, 10% of the.
10%.
It could be definitely. That's a fair question.
You could vary that and just.
But he's got the distribution, right? So
Yeah, that's what I'm saying. So,
he's showing you the range of values. So
I feel like more than yeah.
Oh, sure, because it completes. Yeah, sure.
I agree that more than 900 seconds is a lot. Then I don't know if maybe 90 would be right, maybe 15% would be right. But you can see the paper and be like, okay, this
Can you
is
try to push it further and see if you give it an hour, do you get better reports? All right.
maybe. I think that's not a good evaluation of whether it's performance or not. It's just I'm not gonna. I don't know. If I get an average of 900 seconds, I don't think it's really good. I don't know. Anyway. So yeah, we still get 13. The average time is somewhat low. It's 55 seconds. So yeah. And then one of the things that is cool about these reports, well, in my opinion anyway, is that you can get some value of it by even seeing parts of it. You don't need to get the full report in order to get information. So if you see one trace that tells you, okay, you didn't explore more than the first iteration, and you know that any extension of that trace is not explored, then you're maybe, this is not really good, right? This is not a really good exploration. And what I check here is the time until the first element of either the safe cones or the frontier, the exploration frontier is produced. And what we have here is the combinations of different techniques, right? So we have P stands for predicate analysis and E for explicit value analysis. And then PP means that I ran predicate analysis first, and then I ran predicate analysis for the generation, and so on and so forth. And what we get is that for most instances, we can produce a trace between starting within half of the verification time. Well, you can also check it for like 10% is not great, but you can produce it for many instances with some of those combinations. And then sort of what are the results or the conclusions of the evaluation? Well, the technique that you use for the execution report definitely affects the performance, which is what Tom sort of had the intuition even before I talked about it. And then the running time does not seem prohibitive. I mean, we can disagree on whether it's 10%, 15%, but it's not a multiple of 20 times the verification times. The size of output, on average, is usually fine, but the maximum is definitely not great. What I do, and in order to, that's kind of related to my own inspection of the output, is you can group these traces and sort of abstract them. The problem with that is the semantics is not that clear then, because what is it's an existential semantic on that abstraction, so it means that there's some concrete trace that has been explored or has not been explored, and it's kind of fussy for an end user. But for the purpose of analyzing your output, it was actually super useful. I might write a paper about it at some point, I don't know. Anyway, definition of analyzed. Well, that's a problem with the safe cones. What is the problem with the safe cones? Well, if you look at the assumption automata, sometimes what happens is that trivially by just extending the counterflow automaton from that place, there's no reachable assertion. So those are, by definition, safe cones. Right? And what we're using, we're sort of inheriting our definition of what is analyzed is what we get as the output of conditional model checking. So paying attention to what has been analyzed is part of explaining these inconclusive results, because it's not really trivial to do that. I mean, if you want to explain this to a user, you might want to spend a little bit more time making trivial extensions to your exploration frontier, basically. So yeah, that's kind of a conclusion and sort of future work.
So you're saying the initial model checker was smart, you could have already gotten some more safe zones.
Yeah, if you do, not really. What I'm saying is if you do a really dumb post-processing on the assumption automaton, you can get better results. Sorry.
So it'd be useful to understand kind of what this looks like concretely. Like, you know, if I see one of these traces.
Yeah.
And also it'd be useful to actually understand, were there cases where the trace led you to look at the code and understand why something was analyzable and the other one wasn't?
Yeah, absolutely. So, why it wasn't analyzable? No, but what? So let me explain a little bit about that. I was hoping to talk about that in the questions, but let's talk about it now. Sure. Anyway, so what I did in the first iteration of this paper was go over all of the outputs and check what insights could I get from what I was producing, right?
Right.
And the first problem that you bump into is the traces are huge, so you can't deal with that. So what do? Well, you look at the stack depth, right? Because that gives you an idea of like how far into you're in, right? And you filter some of it because you don't really care about it, and you group them together. Then you maybe have like 150, and now you have 5. And then you look at the stack depth, and you see that you have two methods that are get called in a sequence, and you're like, oh, maybe there's a loop there. I didn't know the instance. I don't look at SVCOM code in my free time, so I didn't know the instances. Right. So what I did was, you have a trace, and then let's look at the code. Where does this method get called? Oh, it gets called in one place. It's the main loop of the program. Now what you see is that your exploration frontier maybe reaches the second iteration of the loop, but you got all of that understanding from maybe looking at one trace and doing grep on the code. If you wanted me to do that by looking at the abstract reachability tree and the code, I don't know if I could have done that. That's what I'm saying. I think it gives you an insight that you couldn't get from just the raw materials, basically. But yeah, you still require some post-processing to make it be manageable, because these are long traces. This is like it has every single statement to make the semantics sort of clearer.
Right. Yeah, I guess I'm trying to understand how it's actionable. In other words, if you give me the trace and I'm a developer, because the way I was thinking about it too is, you could stop and give me this abstraction, and then I look at it and I use my brain to understand what's going on.
Right.
Or you just let the model checker continue to run.
Yeah.
So my brain time is worth a lot more than the model checker, the CPU time. Of the
Absolutely,
model
but how far will you get by giving it like twice as much time? That's an
Right.
experiment that we didn't do and we should do. Actually.
No, but I do think that this question about what's the human process afterward, right? And how long does that take? Because I think that's a fair question.
I agree, it's a fair question. So the way I envision it is you're asking, well, why don't you just like let it run longer? The problem is that if you let it run longer, you're in the same position that you were before, which is, what did it do? Is it good enough or not? Right? And
but it might find errors, right?
It might find errors, but let's consider the case.
But that's what I'm saying. I mean, the comparison is that, and you let it run an hour, it finds something or it doesn't, or you give it to me and you give me an hour. Right?
Yeah.
And what the question in my mind is, will I find errors in that hour, right? I mean, is what you're giving to the human. That I've been spending more time on Excel spreadsheets, it turns out. But the point is, there is a sort of brain, like my brain is doing something when you give me information. And the question is, like, can't we emulate that instead of, when you take that output, I think the computer can understand your outputs better than my brain. But the question is, how do you do that?
Sometimes I think the problem is that it's a fundamentally different task. That's the thing. One thing is to go bug finding, and another one is to define whether whatever attempt that you did was good enough or not. That's the problem. So if you're using, for instance, a static driver verifier, and you reach the whatever bound, iteration bound, and you didn't find any bugs, and you're leading a company that does drivers or does hardware or whatever, how do you know if that's enough or not, or if you need more testing? Should you use only static driver verifier or pay your engineers for an hour of extra testing? Well,
that's a great question. So the key answer, the key question in the research is, how do you take the output of what you have and give somebody the ability to make that decision?
Yeah, absolutely. Yeah. And that's kind of where coverage comes in, right? Because
you didn't mention could have done is, the human can look at it and come up with some loop invariants that if you had written in the original program, the model checker would have just finished.
Mm-hmm. I mean, definitely. If you have that sort of assumes that your user is an experienced user, which I'm trying not to, because that sort of limits my impact. But you can definitely do that.
But I think that, fundamentally, there's this. Anyway, we can go into this offline. But just giving coverage information and saying, well, I got here, is one extreme. The other is you can say, well, at this program point, I learned this invariant. And that invariant might not be parsimonious. It might have all sorts of variables that aren't relevant and confuse the user. But it might be worthwhile persisting that. The user might get some insight. Oh, you discovered something interesting about my code. And that takes up a lot more time than inspecting a coverage report. Oh, you got here, good. Or you didn't get here. So I think there's still a spectrum of information that the model checker has, and it's not exactly clear. There's a whole design space there, right? Because with predicate abstraction, you have these formulas over the predicates. You might have learned interesting facts. Is it useful? Don't know. So I think the reachability tree sort of discards a lot of that, right?
Kind of. I think it depends on what kind of analysis you're using. If you're using a reachability tree, you're most probably not gonna.
Yeah, sure. So let's take it offline. I know.
Yeah.
All right. I think it's a bit.
Yeah. We can talk about it later. Anyway, yeah. So coverage. So one of the questions is, okay, you got that report, and how do you know whether it's good enough or not? Should I stop model checking or not? And an obvious solution to that is, that sounds a lot like adequacy, right? So what's verification adequacy? I don't know. I don't think you guys know either. But can we summarize these execution reports? Is there any way to do that? And then it would be cool if we got some of the users that use coverage. We don't have that many users. So anyway, one of the problems with defining coverage, and you might be like, okay, I'll just output whatever statements I covered. And one of the problems is that, what if you're doing incremental search, right? So you're doing loop enrolling or something like that. And you have this example, right? So this has only one system execution, right? And it always reaches assert false. So we have a verification attempt that unrolls this loop, right, for a number of times, and it takes forever, and I time out, right? And what do I say about that statement? Is it covered? Is it not? And it seems like a kind of trivial question of, well, it doesn't really matter. It's just about a definition. But what if it's a block of statements, right? And this could arbitrarily inflate your coverage measure, right? So there's really no, I mean, this is fundamentally different to testing because you don't know if your verification does not run to completion. Tests do. So you don't know if you reach the assert, right? But that's not the only problem because you might be telling me, oh, I don't use that. I don't know. I don't use incremental search because that's not efficient. I use modular analysis, right? But the problem is you're probably using our approximation because you have infinite state spaces, you have state explosion, and if you don't use over approximation, your model checker doesn't scale either. So you have this problem, right? And you have reached dead code, which obviously is dead code. And you find you're using predicate abstraction, and you find a counterexample that's spurious, right? Because you were not tracking the predicate. But again, we have nonlinear arithmetic. Your model checker gives up there, and internally, its abstract reachability tree, for instance, would have that statement in its representation, right? And well, should we consider it covered? Does it count towards the coverage count or not? Well, I don't know. Those are decisions that people make, and I made my decision. My decision is basically, this is sort of a general framework. This does not actually tell you what any of the previous examples should give you. But what I tell you is you need basically some terminating execution, right? And why some terminating execution? Because that's a way to work around the problem of verifying, of checking whether you've checked an assertion or not. If you have a terminating execution, well, if your code had any assertions, you're going to reach it, right? That exercises the statement S within an analyzed portion of T, right? So that whole predicate, I'm not telling you what it is because it depends heavily on what technique you're using. And I'm going to talk about it in the next slide for abstract reachability trees, right? And then I asked that the terminating execution is actually safe because if I found a counterexample, I shouldn't be computing coverage. I should be fixing the bug, right? So what does it mean for abstract reachability trees? Well, first of all, why abstract reachability trees? Well, because I was working with that, and it makes sense as a first step. But actually, in our paper that we're going to get feedback tomorrow, we talk about some extensions of this for other techniques, sort of on a high level. And then what does it mean for abstract reachability trees? Well, we offload the whole, has it been analyzed to the conditional model checking predicate psi, right? So when has something been analyzed? Well, it's been analyzed if it reaches only nodes outside the abstract reachability tree wait list, right? So remember, we talked about the trees. We have wait list, which correspond to stuff that hasn't been explored yet. If you reach one of those, well, then it means that you've gone outside the analyzed space, right? If you haven't reached one of those, then you remain within the analyzed portion.
What is P here? Is it a state?
No, I didn't explain that part. So what we have is some terminating execution T. We have P, which is a prefix, right? And it's an analyzed prefix, so it remains within the abstract reachability tree. And the statement is within the prefix of the terminating execution. So this kind of raises the bar a little bit for verification techniques because you not only have to have it within your structure, your internal representation, but it also has to be part of a feasible execution. And sorry, I don't know what it was. Anyway, so research questions. Is this can I produce a reasonable under approximation of this within the original verification time? Again, why do I have to under approximate it? Why don't I compute the exact coverage? Well, because that's probably not computable, but I mean, I don't know, it can just time out. You don't know how many system executions you have. Anyway, so we produce
It can't just be done online while you're checking, given the property?
I mean, kind of. You need to, it depends on whether you have system executions or not. If you have terminating executions, you can just check how much of that you cover. And that's one of the use cases that we consider. But that would be an unfair comparison because I would be like, oh, I computed on the fly. Well, but you need to have those system executions so that you have to pay that cost at some point. So you have sort of those system executions. Yeah.
Because it's.
So what I have is a terminating execution T.
Yeah, you don't know. I sorry, I forgot about that.
I need sort of.
Yeah, okay, sure.
I need sort of a witness that this is an actual system execution. That is not just
I get you.
made up state space.
Yep.
So anyway, so that's one of the research questions. And then the other one is, Well, but do model checkers actually cover any code? Because nobody checked. So, so what we do is, ideally, we would want to write manual tests and compare the coverage of that with our model checker coverage. But that's kind of like apple and oranges. Like, how do you compare the effort into going for both things? So what we do is compare it against the automatic test generation tool like CLI. Here, the architecture, same case as before. We have a code, then we have the software model checker that produces the assumption automaton. That's the condition side that conditional model checking talks about. Then we have this whole pipeline, and then it's a loop, right? We have on the far left, we generate a specification that captures the sort of properties that the terminating execution will have. Then that specification is fed into another software model checker, it could be a different one. And that software model checker produces those safe terminating executions that might have additional properties or not. And then we take those safe terminating executions and we check how those executions are covered by the condition psi, right? Then we update the coverage statistics. And then we feed those back to the specification. Why do we have that feedback loop? Because for instance, in CPA checker now, you can give it a specification that tells you, okay, I want to cover this one line in particular. So every terminating execution that we generate is the terminating execution that increases the coverage, which might not be the case.
And these are terminating execution that has a witness that the spec was correct.
Yeah.
It's not just random terminating execution.
No, I mean if you produce a bug or a counterexample, you report the bug, yes. Which could happen and actually does. It's in the evaluation. So what do we do? Same instances. Sorry.
In the case of CLI is not assertion guided, right? It would just produce random paths, right? It's forcing CLI to go through the assertion.
I think it has two modes. I think it has two traversals at the same time, and it does a round robin. I don't really know the details of that. But anyway, yeah, CLI will not give up. If it finds an assertion, it will continue producing test cases. It doesn't really care. It will report them, but it will continue producing test cases. So we use the same instances. Phase 1 is the same thing. And phase 2, for those with inconclusive results, we compute the coverage, and we create a test suite using CLI. And we duplicate the time spent, right? Because, well, we're not just verifying, but we're also computing coverage. So CLI, to be fair, has double the time. So do we produce a reasonable approximation within the original verification time? Well, let's look at the techniques separately. So we have value analysis. And I should have, this is the wrong way of showing this. But anyway, so for 5 of the instances, we produce an under-approximation that is between 40 and 87% of the over-approximation. Let me talk about what the over-approximation is. So CPA checker already produces a coverage statistic. But how does it produce it? Well, remember those problems that I talked about at the beginning? That maybe you would have code that's not reachable, and maybe you would have prefixes that would trivially lead to false assertions. Well, that's how they produce it. So it's a very coarse over-approximation. But we don't have the exact message, so we use that. Anyway, so in this case, it's not ideal, but I mean, it's for more than half the instances we produce a reasonable under-approximation. And then for 2 of them, we find bugs. So then we give up on the first, so only for 2 instances, we don't really produce anything useful. Then for lazy break,
What does it mean not useful then?
Huh?
What does not useful mean?
That we don't produce anything. For 2, we don't produce output. That's the definition of not useful.
Because you time out, or?
Yeah,
No,
we time out producing.
the same result that CPA, whatever.
Yeah.
Oh, okay.
No. CPA checker always gives you an over-approximation
Yeah,
because you
that's
get.
what I was going to say. So
it's
that would be
essentially
another way to not be useful.
Yeah.
But this 87% is not meaningful because an over-approximation doesn't give you much insight, right, of coverage.
No, but I mean, if you always get 0% or if you always get 10%, then it's really bad. If you get 87%, you're pretty close to the actual number. Then for lazy break abstraction, then you got 16 instances, and then for 11 of them, you give something that's between 55 and 100% of the over-approximation. For 3 of them, it's special cases, basically. One of them is 0 coverage because the exit is actually unreachable, whereas CPA checker would report 267 lines of 388 covered, right? So that's how inflated the coverage could be. Right. For another one, well, you have a bug found, so I mean, it doesn't really make sense to compute coverage. And for other one, we get an abstraction refinement error, which is basically something that we could work around. I mean, it's just we chose the wrong technique maybe, but it's not absolutely unworkable. And then for 2, we produce a completely useless result, which is nothing. But then, how do we do compared to test case generation? Well, for 15 out of 23 instances, software model checking coverage outperforms CLI coverage. And moreover, for 6 out of 23, which is more than 25% of the instances, we're a multiple of the coverage that CLI produces. And only for a couple instances, we do get smaller coverage. That's it's less than 80% of what CLI covered. So that's pretty much the conclusions of the coverage part. And I just like to summarize a little bit of what I've talked about during the talk, and talk a little bit about future work, which is, I think, kind of interesting. So basically, key takeaways, focus on inconclusive results. I think that's super interesting. Having formal guarantees for the output also is super interesting so that users can know what to expect about it. Then building a proof of concept and evaluating it can give you insights. I think that's interesting and that's super relevant and you need to do it. And then for execution reports, basically the key contribution is just the idea of producing these safe cones and expiration frontiers with concrete guarantees that make it easy for your users. And then coverage, the contributions are the overview of the challenges, then a measure that can be compared to test case generation. That's useful. Anyway, future directions, short term, stronger guarantees for coverage, that would be cool. Because I have the intuition that there's something about the breadth of a verification attempt that we're not capturing by using the same semantics that you would have in test case generation. Then improving usability of reports is what you mentioned. It's long traces. We have to pay attention to that. We have to find a formalization that makes sense and that's still intuitive for users. And coverage and reports for other techniques, we talked about this a little bit in the coverage paper that we wrote, but it would be interesting to implement it and actually test it, because we don't know what the coverage is for many things, and it would be interesting to know it. Then technique and time limit recommendation, that would be basically, now there's tons of portfolio approaches to sort of statically choosing the best tool for a certain instance. And you use structural features such as, do you have loops? Do you have floating point? Do you have pointer arithmetic? Stuff like that. And certain tools are better for this and they're better for that. But what if you have a short list of 4 or 5 tools and then you run them in parallel and you can prioritize them, but looking at their intermediate results? Now that we're getting more insights into this, I think this is an obvious next step. But what about longer term? Well, I'm mentioning again coverage and intermediate results for other techniques. And why am I mentioning it again? Because I think we can take the path backwards. If we had a representation that's actually shareable between different techniques, such as coverage, you could have much more aggressive unsound assumptions, right? Because it would make sense in that context to provide techniques that can increase the coverage, right? Because this coverage is useful. I think this could lead to entirely new families of techniques that would make sense in that context, and that right now might be too specific and you might not have a concrete use case for them. Then a special case of this is angelic verification, right? So you might have a very demonic environment, and what you're trying to do is filter all those false positives, right? And correct me if I'm saying anything wrong because you're here. But one of the things that you can do is sort of make these two things work together. What if you could, instead of filtering out certain specifications, what if you could rank them using coverage as a proxy for how reasonable or unreasonable they are? And then, well, of course, we have to conduct large-scale studies, basically knowing whether the results for test case adequacy hold for verification or if they're different. Then building other types of reports would certainly make sense. What I've commented is only good for abstract reachability trees, but if you're doing modular analysis, all of that breaks down and it's not really useful. Then user studies, because that's basically the only way to validate that what we're doing makes any sense. And I think tool integration is basically the step forward to get all those ideas and making that vision that I talked about at the beginning at least closer to true. So that's all that I had to say, and thank you very much for your time. All right, we'll talk later.
So I just have one question. Obviously we have SLAM and as data forever verified here. So we're using this model check to actually do stuff with software. Is there an equivalent kind of effort externally in the open source community? around using, because I guess one question I had would be, like, what's the path to your, most immediate practical use of this?
I think the path to the most immediate practical use of this is basically that, integrating some of these tools to an IDE. And I think the obvious place to do that is Visual Studio, because
But you have to start with a developer community that's actually doing this in some way, right?
well, that's what I'm saying. So you already have all those tools integrated into Visual
we
Studio.
do.
Yeah.
So Microsoft does. I'm just curious if anybody else does.
You don't. At least that I know of, there's nothing like that. There's similar stuff, and there's static analysis integrated, but it's more like pattern matching certain smaller things, and it's more lightweight stuff. Then you do have some concerted efforts into, for instance, like the Linux driver verification effort. But all of that is usually using one or two tools, and it's a very closed community. It's not. I don't think the Linux driver developers are using that. I think it's the other way around. It's just a more closed verification community trying to find bugs in Linux drivers.
I see. Right. So it isn't the developer community sort of pulling; it's the verification community pushing. Basically.
I mean, it kind of makes sense because, like, if you're not providing something that can give consistent value, why would your developer use it? I mean, I don't think there's mature tools.
It's pretty clear on the Microsoft side that it does add value, right?
Yeah.
I mean, it's been used for like 10 years, right? So I'm just curious that even though we've been doing this and shown that actually it adds value, why or where it's sort of this kind of effort is actually taking place externally.
As far as I know, there's no other place in which it takes place. I think there's a few reasons why that's the case. I know we can talk about it offline, but
Sure,
I think
One of the reasons could be Microsoft invested a lot before starting to see value in the SDV space.
Yeah.
Sure.
I think it's a significant investment.
But also so static driver verifier, for instance, it's a use case. I mean, it's not, you can't replicate that anywhere else because you don't have outsider companies writing. I mean, you don't have you don't have a company with control over Linux that can sort of give those
central
tools.
authority for
Yeah.
But you'd think that in the end, a tool chain around doing model checking, right, for a particular class of problem like finding bugs in drivers would become widely used. It just I think one of the things that's interesting, Microsoft had a real problem with drivers, right?
Yeah.
This issue of the machine crashes and you blame it on Microsoft, right? So we had a very strong incentive to not have that happen. But you think the Linux community would have the same problem, right? Is that when something crashes in Linux, it's like, why? And well, it's a driver which is bad, right?
Yeah, I don't think there's significant pain points, and it's the problem is basically your community is different. Like if something crashes in Linux, I just downloaded something that a random guy wrote somewhere. I didn't pay for this, and I was like, I'll fix it. I'll figure it out. I don't know. I guess it's different for a company, and there's no really great incentives for anyone to invest in that, basically. So I think there's compelling reasons why that doesn't happen outside Microsoft.
All right, well, we can talk later.
All right.
We're going to talk to
Thank you very much.